Welcome back. We should continue. And our only speaker before lunch is Henry Legg from Basel, from my old country.
Well, good morning. I'm Henry Legg from the University of Basel, and I'm going to talk about Majoranas. We also heard in the last talk about Majoranas, but the Majoranas I'm going to talk about today are quasi-particles that form bound states at the end of a system like this, where you have a semiconductor nanowire, you proximitize it with a superconductor and apply a magnetic field. And the idea is that as a result of this applied magnetic field, you can make the nanowire go into what's known as a topological phase. So you have a topological phase transition, and due to the inherent particle Hall symmetry of a superconductor, the Majoranas appear as zero energy states at the ends of the localized at the ends of these wires. So that's the idea, and there's been a lot of interest in this system in the last decade or so. And one of the reasons for that is there's a proposal that you can use this for what's known as topological quantum computation due to the localized nature of the Majorana. So as a result, there's been lots of interest also from the industry side in such a setup. Now, originally, one idea to probe this was by essentially a very similar idea to STM. You attach a normal lead to your wire, and you ask whether or not I can tunnel into the wire. And very similar to STM, you measure the conductance as a result of that. And because this Majorana is supposed to be localized at the end of the wire, you're supposed to see a zero bias conductance peak after you go through this topological phase transition. And there was a lot of excitement. Some of the authors of the paper are in this audience when in 2012, such a signature was observed that you apply the magnetic field to such a nanowire, exactly this setup with a superconductor attached, and you saw that there was some zero bias peak appearing. But subsequently, it was found that actually these zero bias peaks are not a smoking gun signature of Majoranas, and there are many other ways that we can get them through just trivial means, much less interesting physics. Still, to some extent, interesting. It's still about superconductors, but much less interesting physics. So one of the most boring ways is just due to disorder. You can also have things like quantum dots that naturally form at the end of these wires, and also smooth potentials. It's just some examples of how you can get such things trivially. So this is well known, and there's been a lot of interest in this in the last decade. So as a result, the community started to think, what other signatures could we look for? One idea was, for example, seeing oscillations. When you apply a magnetic field, then these Majoranas should overlap differently, and they should then move away from zero energy and oscillate. Another idea that became popular due to mostly theorists was looking for quantized zero bias peaks. So you think of something which is topological, and most theorists think of, say, the quantum Hall effect, which has a quantized conductance. And in the case of Majoranas, there should, at least in theory, be such a thing, which here is a conductance which is at 2e squared over h. And there was indeed a paper that claimed to have observed that, and probably you will know the story behind that. I'm not going to talk about it today, but eventually that was actually retracted. So this idea of looking for more signatures, different ways of seeing, do we really have a Majorana? Is this zero bias peak actually a Majorana? I think it's a good one, but the question is, what signatures should we look for? And another idea which became prominent in the last couple of years, particularly from Microsoft Quantum, was looking at what's known as the non-local conductance. So this essentially takes the same setup that we started with in the first case, but now we add a second lead on the right-hand side of our wire. And in such a setup, we can not only ask about the local conductance, so whether or not I can tunnel into the end, but also whether or not a charge can go through the wire. Now, because it's a superconductor, that charge can either come out as an electron or a hole, but the details are not so important here. The idea is that this non-local conductance, whether or not I can go through the wire, measures the extended states within the nanowire. And when we have a topological phase transition, at least the idea is that these extended states will appear in the non-local conductance. And so we can see this phase transition when we go into the topological phase. And that's because, again, that these states are extended, the ones that cause this phase transition. So Microsoft used this as a basis for what they called their topological gap protocol. So the idea was look for zero bias peaks on either end, and then look for this gap closing and reopening in non-local conductance. I should say that already that this is not a necessary signature of Majoranas or a topological phase transition. depending on the junction, you can actually find situations where these extended states do not show up in non-local conductance. So it's not necessary to actually see this signature, but you can also ask, is it sufficient? And that was kind of what we decided to do, was just ask, is there some trivial way that you could get such a signature without having this exotic topological physics? And I think the answer is pretty simple, and it's yes. It's that all we need is an extended state. And the idea is that if I have some localized states, they overlap in the bulk of the nanowire, then I can get a non-local signal that goes through the wire. And this can mimic this gap closing and reopening that was supposed to be from a topological phase transition. And we showed that you can add zero bias peaks on top of that. Many mechanisms are known for zero bias peaks, as I said at the start. And also that this can tolerate quite a large amount of disorder, for example, in the position of these bound states, these states that I use to form these extended states. So this physics is, I think, pretty well known, actually. It's essentially impurity band physics. I just have some bound states, some localized states, they overlap, and that allows a conductance through my system. And we were quite happy with that. We thought that this showed that this was not such a robust signature of Majorana's, and the reviewers at PRL and also the editors, actually, we ended up editor's suggestion, agreed with that. Simultaneously with that, Microsoft went ahead and now put out a paper where they claimed that they had passed their gap protocol. There was a lot of fanfare around this, both from the media side, also from Microsoft. They were very happy. They said, for example, that it was akin to inventing steel. So they were obviously, they thought that this was a big result. There was also some editorial parts to this. I'm not going to go into that right now. But they claim now that they passed their homework and that they'd seen both this signature and they'd finally seen the Majorana's. And in particular, something which we found a bit confusing was that in this paper, they state that they see 0 false positives. So what they do in this paper is a load of simulations, theoretical simulations, and they state that they see something like 600, and they never find that the gap protocol gives them something which was not Majorana, so which was not topological. And we found that quite confusing because we knew that there was quite simple physics going on that could cause such a false positive, or at least could reproduce all of the features that were required to produce a false positive. We're even more confused then when later in that summer, Microsoft decided that they were going to put a comment on our paper where they said that the mechanism that we proposed would not cause false positives in their gap protocol. Now, already this comment had a bit of a strange logic. They did a single simulation, which was shown in their figure 1. And they claimed that because this simulation, according to them, failed the gap protocol, then it proved that this mechanism could not cause false positives. We obviously decided then to look into, so the gap protocol by that point was publicly available. We started looking into it, and we found it was actually very easy using our mechanism to cause false positives. And so you can read our original reply online. We show several different ways of getting false positives. But as we learned more about this gap protocol, we became a bit confused. Why, even in this case, this single simulation that Microsoft showed in this figure, why it was not passing? Because we could see by eye that certain regions should actually have passed their protocol. And so we requested the data from Microsoft directly. And by that point, they went quiet. They didn't respond to us. But luckily, Microsoft had also submitted this comment to PRL. And I have to say a big thank you to the editor at PRL, who eventually was able to get Microsoft to give us this data for this figure, this one figure in their comment. And of course, so just to say now, this was the claim from Microsoft, and they were very explicit about how this was done. It was using one junction configuration, even at 40 millikelvin with their broadening. And this was the outcome. That was their claim. So we ran the code exactly as they described. And we found at that point, actually, not to our surprise, that indeed, that even this single simulation from Microsoft passed their gap protocol. And indeed, actually, it passed in 4 different regions. Now, you might see that these regions are very small, but the idea of this gap protocol is that if the protocol says that it's topological, then it should be topological. I'm not saying I agree with that, but that's the idea of this whole protocol. And so we found here 4 different things which we know are false positives because the system is trivial. There's no spin-orbit coupling. There's no Zeeman energy. But yet they're passing this protocol. And just to remind you, Microsoft's claim was that this simulation failed the GAP protocol. So in the end, all we actually submitted to PRL was this figure. And I was very happy that in the end, this comment is now no longer under consideration. You can read our full comment, our full remarks on the comment under this archive link. So just to come to my conclusions on this part, I think that there's a scientific one, which is that this GAP protocol, which was quite hyped, is not sufficient, and it's also not necessary to detect a topological superconducting phase, to detect these Majorana-bound states. I think there's also one on reproducibility and integrity, which is the title of this conference, which is that I think it's a good idea to start looking for more signatures to become more confident that what you're seeing is what you expect. But we should also, it's a legitimate question to ask how reliable is a signature. And I think in any discussion about that, then we should discuss this openly and honestly. But I want to also today talk about some more concerns I have about this GAP protocol. And this essentially came from the fact that I started learning how the code was working, and then the data is available on Microsoft's GitHub. So one aspect of the GAP protocol that is strange is that it includes parameters which are not physical. So for example, one parameter like that is that the pixel size matters. So what does pixel size mean? It means the rate at which I gather my data. And this varies massively between the different data sets of Microsoft. And why is that concerning? Well, if I change the resolution, if I change this pixel size in Microsoft's code, you can change something from being a fail in the GAP protocol to passing the GAP protocol just by changing the resolution. So here is an example on simulated data, because there I can change the resolution. And if you look into the different pixel sizes in Microsoft's data that they made available, what you'll find is there's an almost order of magnitude difference between the different data sets for the different devices. So each of these is a different device, and this is the different sizes of the pixels. And indeed, the pixels for the experimental devices are almost always smaller than in the actual simulations that they did, that they claimed that they had 0 false positives, that they claimed as the basis that this would now be a reliable signature of the Majoranas. Something else which, as I was looking into the data, started to concern me is that there's a strong dependence on the cutter voltage. Now, what that means is just at the end of my wire, I have a small voltage I can apply to change the barrier. So that shouldn't change really very much, or it shouldn't change anything about the bulk. And the idea is that the bulk of this wire, this non-local conductance, should be a measure of that bulk. But what you find actually is that in Microsoft's data, you can get situations like this, where I go from a situation where I have a gapped system. I just change a small voltage at the end of the wire. They completely change what is seen by the GAP protocol. Here, now the GAP protocol, the orange stuff is the one where it sees it as gapped and 0 bias. Here, it's yellow, and it sees it as gapless. So just by changing this small local cutter gate voltage, according to the GAP protocol, you can completely change what whether or not my system is gapped or gapless, what's happening in the bulk, according to the GAP protocol. And what's a bit concerning about that is that in the paper that was eventually published, only the comparison for device A1 is shown. Whereas in all other devices, there is at least one cutter gate where you find such a situation that makes the device fail the protocol. And then finally, something for the theorists, but I think we can all appreciate this, is that the definition of topology is significantly loosened in the eventual published paper compared to was the original idea, which was posted on arXiv in 2021. And the definition in this original paper was that you have some determinant of a reflection matrix. The details are not so important, but it's less than minus 0.9. Whereas in the final published version, you have this determinant just less than 0. And also that it can be on either end of the wire that it's less than 0. You can have it positive on the other end. It just needs to be in a single pixel for that identified region. And it just needs to be for a single cutter gate, one of these small voltages at the end of the wire. And so now it starts to become clear why you get 0 false positives in the simulations, because you get a situation like this, where this is seen as a true positive according to the gap protocol due to this single pixel here, which has this determinant of the reflection matrix being less than 0. And in this case, it's also just on one end of the wire. So this is considered a true positive in the gap protocol, despite the fact the majority of the region which is identified by the gap protocol doesn't contain Majoranas and is not topological, even by their very weak definition of topology. Sorry, it's these hash pixels are the ones that are topological by this definition, and it's not necessarily by anyone else's definition. The whole orange region is counted now as topological and counted then as a true positive rather than a false positive. So, okay, I think that's a discussion which will be had in full at a different time. But I mostly wanted to talk about this situation with the comment, and so I'm happy to answer questions.
Very much, Henry. Yes.
You mentioned you were happy to see that this comment was rejected basically, but I mean, that means your reply also doesn't come through. And I guess I'm wondering if maybe science is better served by these things showing up in the literature. I mean, I know they're on the archive, but maybe people saw only the initial comment and they said, oh yeah, those guys bungled. Now there's nothing official. What are your thoughts on that?
But it's a very good question. I would have actually, in the end, I think I would have been happy for it to be accepted, because I think that there would have been a good case for retraction, which would have been even better. But in the end, it just wasn't true, and I can now talk about it in this type of forum. But I agree with you. It would be a good idea if there's some other way of getting such messages out.
I guess the stakes are a little bit different for, let's say, Microsoft versus, I'm trying to think of a comparable university institute or something. Could you comment on that and how this is affecting how this plays out?
I'm not sure I fully understand it.
Well, it's a private company, so they're protecting, I don't know, everything from shareholder price to whether the group exists next year, I suppose. I don't.
So I don't know why this happened, but I guess, yeah, there's certainly sociology that goes on when companies are involved.
First of all, of course, I fully agree. I mean, the share price of Microsoft may be affected if their research on quantum computing is exposed to fraudulent. Of course, they have stakes there. But somewhat related and a bit provocative question. Do you think that that part of what is going on, we see several talks relevant for our discussion on this specific subject, on these Majorana things. Do you think that maybe they have been given too much attention in general, regardless of whether it's fraudulent or not? Yeah, do you think that this Majorana problem deserves that much attention as it has? It's a little bit sidetracking, but I'm just curious.
It's a good question. I think that firstly, it's attracted a lot of money, so that's one reason why it's been so prominent. I also think that a lot of it comes down to device physics. Most of these Majorana stories require devices, and device physics is complicated, and it's also easy to trick yourself. And also, I guess it's also to trick other people if you want to.
Igor, I'll cancel my talk, and it's all the fault of the theorists. No, just joking. I was wondering, you talked about code from Microsoft, etc. Did in this process of the comment, etc., did additional materials shared with you compared to what was made available upon publication?
In terms of the comment, they did make eventually through their GitHub, they made the data and the code that they provided some code to reproduce this figure. But that code has, well, we can go into the details about what happens with this, but basically they pad out their data with things that aren't in the figure, and that makes it look like the code is working, but it's not. So in that sense, yes, in the end, I think an interesting part of this story is that the PRL editor did a really good job. He helped us get the data from Microsoft. And in the end, that's how we were able to show not only that you can cause false positives, but that this original simulation was not as described.
So just for me to clarify, at this point, have sufficient materials been shared, in your opinion, by Microsoft that you can fully reconstruct what they did in the published PRB?
No, sorry, I was talking about the comment. So they provided more details.
Yeah, sorry, this was a sort of a follow-up question.
Yeah. Yeah, for the PRB, I'm the same as you, that there is data online. I don't believe it's the primary data, as we heard in the first talk today, but there is data online. But there's a lot of data online, and then you have to go into those details. But there's no extra data that's been shared with me compared to what's available to everyone else.
Okay, let's thank Henry for this presentation, all the speakers of this morning. I pass the micro to Sergey.